Hello everyone, this is Frank Custis. I'm the Chief Technology Officer with NanoCoatings, and today I'd like to present the results from our Phase 2 SBIR program with the Navy entitled All-Solid-State Battery. This slide gives a brief introduction into NanoCoatings. Our focus is the use of thin film deposition technologies for solid-state battery materials as well as coatings for friction, wear, and corrosion reduction. We also have some wear testing services that is used by some of our customers. Since our inception in 2012, we have won 7 Phase 1 SBIR STTR projects, a singular Phase 2 SBIR, which is this project with the Navy. We have worked with the Army's Future program. We were selected to give a presentation and given a cash award for all solid-state batteries. We've worked previously with armor coatings and armor systems. We have an Air Force Phase 2 SBIR pending, as well as a DOE Phase 1 and a OSD Phase 1 pending. We are also in the process of preparing a patent for the fabrication of all solid-state batteries by physical vapor deposition. Key personnel shown here include myself as the Chief Technology Officer. I have over 40 years of advanced materials experience, ranging from startup companies all the way up to a major defense contractor, Lockheed Martin. Our key processing lead has been changed. It's now Kelsey Fitzgerald. He is a Master of Science candidate at the School of Mines. He is responsible for PVD processing and also high voltage anodizing using a technique termed plasma electrolytic oxidation. Kelsey is also responsible for friction wear testing. From time to time, we will hire undergraduate students from the School of Mines to assist Kelsey. Our laboratory is located in the Ascent Innovation Center, which is located next to the School of Mines up in Rapid City. We have 3 PVD chambers with different processing capabilities and scales, a PEO station for the high voltage anodizing work, as well as 2 friction wear test machines, which are used in testing services for customers. We're also an associate member of a pending School of Mines NSF Center for Green Solid-State Electric Power Generation and Storage, which we hope will be awarded soon. The requirements for our Navy Phase 2 program, all solid-state battery, are shown in this chart. Currently, the state-of-the-art lithium-ion batteries have a liquid lithium electrolyte, which is subjected to thermal runaway, fire and explosive hazards, although this has been mitigated somewhat in the last few years with integration of a battery management system. But our goal is to develop more reliable batteries with solid-state electrolytes, which will eliminate that safety hazard altogether, and also increase the performance with higher specific properties for naval aircraft. The expected transition target are for fighter aircraft, emergency power and backup electrical power, which have 24-volt output, and engine start, which is a 270-volt output. Our goal is to exceed the performance of conventional lithium-ion batteries, but under safer operating conditions. We're also tasked with making a prototype battery with an integrated battery management system. The milestone for this is the middle of March 2021. This chart shows the operational needs and improvements that the U.S. Navy is expecting from us on this project. As I mentioned in the last chart, lithium-ion batteries have safety concerns from the organic liquid salt electrolytes, and the replacement of those with a solid-state material should eliminate the flammability, volatility, and corrosive nature of those electrolytes. They will ensure the safe operation and longevity of the batteries. These new solid-state batteries must exhibit higher performance, for example, 200 watt-hour per kilogram energy density, power density of 1.5 kilowatt per kilogram. The batteries for the fighter aircraft, once again, are for emergency power and backup at a 24-volt level and engine start at 270 volts. There also are a host of other potential applications for these solid-state batteries in unmanned aerial vehicles, communications, command and control, as well as wearable garments for soldiers, since we are depositing these on flexible substrates. Our solution to the problem of flammable and volatile lithium-ion batteries is to use solid-state materials. We have selected a superionic lithium antiperovskite material as our solid electrolyte, which has the highest lithium-ion conductance of candidate solids shown in the upper right figure, including garnets and sodium-containing electrolytes, and lithium ion transport that is consistent or possibly exceeding liquid electrolytes. To do this, we're using a novel radio frequency powered physical vapor deposition method of the electrolyte, as well as a cathode material using state-of-the-art lithium iron phosphate material to reduce the thickness and weight of these layers. In the middle figure shown on the right, you can see the two different plasmas, two different colored plasmas. On the other side of a specimen holder plate, we have a foil on the other side of that. We're doing co-deposition of cathode and electrolyte material and then finishing with pure electrolyte. We have also done some, the School of Mines has performed charge-discharge testing on coin cells. These are CR 2025 geometry, and you can see in the figure, lower left figure, that our voltage range for each cell has been 2 to 4 volts charge-discharge, a specific capacity of up to 400 watt-hour per kilogram, although this is at a 0.4 C charging capacity, charging C rate. For discharge rate, we're at about 115 watt-hour per kilogram at 1.2 C, so we're slightly lower than the Navy requirement, but we feel confident that we can get there. And these specific capacities do exceed competitor cells. Our current status and milestone chart for this project are shown in this slide. We are currently optimizing and testing coin cells with the ultimate goal of incorporating a number of uniform cells into a prototype battery with a battery management system. This has been delayed to mid-March of 2021. Milestones, the 4 milestones shown below. When we first started the project, we found that we could not procure PVD sputtering targets of the materials that we desire from U.S. vendors. So we had to leverage some IP from Los Alamos National Laboratory and a research license. In this research license, it describes the technique for using precursor powders and then performing hot pressing. We have been able to do this successfully, and the measure of success has been the survival of these targets during RF-PVD processing. We also have been performing PVD co-deposition of cathode and electrolyte materials instead of just layer by layer. The purpose here is to increase the amount of active material in the co-deposited layer. Performance has been measured by electrochemical means by the School of Mines. We're also fabricating multiple reproducible cells now using larger area substrates, for example, 3-inch by 6-inch, from which we can get 10 to 12 coin cells per deposition run. The measure of success is measuring the open circuit voltage and then the cell internal resistance, impedance, and then doing some C rate testing. Well, once we have enough cells that have a reproducible internal resistance, we're integrating those, selecting those and integrating them into a prototype battery enclosure, and then using a BMS system to give us the voltage output and the state of charge. And as I stated, this will be completed by mid-March of 2021. The key features of our technology are shown in this chart. As I stated earlier, we're using the highest lithium-ion conductance solid electrolyte, lithium antiperovskite, as our solid electrolyte material. We're performing RF PVD processing of cathode and electrolyte plus electrolyte layers, which enables the fabrication of very thin layers, typically 1 to 2/1000ths of an inch thick, which are not available by the other fabrication methods, including slurry preparation and spreading with a doctor blade. What this enables is the fabrication of very lightweight battery materials on flexible substrates, which increases the specific capacity and could even eventually be used as conformable wearables for the soldier. The table below shows some of the data that's been obtained in the open literature. In the second row is one of our cells from PVD B83, a CR 2025 cell. we can see that our capacity is approaching 2 times the capacity for the leading front edge LiPon cells, and this is with a much thinner layer. We're talking about one mil or so, 1,000th of an inch. The specific capacity, as I stated earlier, that's 400 watt-hour per kilogram. That's under charge conditions. Under discharge, we're at about 115, so we got a little bit of work to do in that range. But by increasing the amount of the active material, active cathode material, we should be able to get there. Our approach and remaining tasks to transition this technology to the fleet are shown in this chart. The requirements do call for high current battery output. In order for us to get there, we will have to do one of two things: either integrate parallel wired coin cell sleeves into the battery architecture, or increase the amount of active cathode material in the layers. And we're looking at both of these options. We will be required to do higher fidelity testing of the high current battery, including traditional charge discharge, state of charge status, and BMS control of the battery. We do require the battery to be exposed to a carrier environment, followed by some testing. The primary transition advocate is NavAir for fighter aircraft, as we stated, for emergency backup power and possibly for engine start. Secondary target is for the U.S. Army and also some commercial markets. This chart shows the substantial market for all solid-state and lithium-ion batteries. Current estimates are that for the solid-state battery market, it will increase by about 7.5x, up to nearly $500 million by 2027. If some of these solid-state batteries can make it into the traditional lithium-ion battery market, then it could take a bite out of this $94 billion projected market by 2025. Some near-term opportunities we envision include for biomedical devices, unmanned aerial vehicles, RFID tags, smart cards, etc. And once we get to a higher current output battery, then the market would increase for electric vehicles, automation, and power tools. Our transition plan is shown in this chart. Our business model includes IP protection, first by trade secrets and then by patent submission. As I mentioned, we are presently preparing a patent for the PVD deposition. Once this has been obtained, then we can license this technology potentially to prime contractors like battery manufacturers such as Saft or Eagle Pitcher, or to larger electronic PVD vendors such as vendors that make solar cell materials. They already have the infrastructure in place, and this might be an ideal transition partner. Other candidate transition paths include the U.S. Army for the next generation combat vehicle, communications command control, and conformable wearable battery for the warfighter. We do feel that by using a roll-to-roll processing or linear PVD system, we can significantly increase the throughput and reduce the material costs, which make this solid-state material much more attractive for commercial applications as well. In closing, we'd like to discuss what your needs and requirements are. This is the contact page for myself, my email address, phone number. We also have a website in which we have a contact page, and I do have a LinkedIn profile that will be made available on some appendix charts. I think that what we'd like to leave you with is that we feel that the all-solid-state battery technology that we are developing will be much safer and offer higher performance than conventional lithium-ion batteries. Thank you.